Welcome to EDU World Space.
Problem 770, we have a small block of a certain mass. It slides in a vertical circle of radius half a meter inside the circle track. And during one of the revolutions of the block at the bottom of the path, it has a normal force directed upward. That's the contact force between the block and the surface that pushes the block away from the surface, so it's directed upward. And we have another normal force at point B that acts on the block, pushing it down. So that's a contact force between the surface and the block that keeps the block away from the surface. And we're asked how much work is done on the block by friction during the motion of the block from point A to point B. Okay, so this immediately tells me by how much work is done by friction that I'm going to set up a conservation energy formula. So initially, I have the kinetic energy due to block, and we're going to define the bottom here to be the gravitational potential equal to 0, so that there's going to be no gravitational potential at the point A. Then we're told throughout the motion there's going to be work done by friction, so we're going to have minus work due to friction. Actually, I'm going to write that as plus, and then that's going to be equal to the kinetic energy of point B. So I'll write that as 0.2. And then we're going to add the gravitational potential energy. So that's going to be plus m times g times 1. 1 here because we have radius of half a meter, so 2r, the diameter from point A to point B, is going to be 1. Okay, so I have K1 and K2 I need to find in order to find what our work due to friction is. So in order to do that, I'm going to set up our sum of forces of acting on these blocks at their respective points to find their accelerations at each of those points. And then that will get me to the kinetic energy at those points too. But I'll show you how I do that. Okay, so our sum of forces at point A is going to be equal to our mass times our acceleration at that point. Now, our acceleration at the point is going to be the centripetal acceleration directed inward, keeping the block moving in a circle. So I write down what the acceleration is, and that's going to be velocity at A squared over r. And I notice that we have mass times velocity acceleration velocity at point A squared, and that looks somewhat similar to what we need for kinetic energy. So I'm going to find what the sum of forces is and then manipulate both sides such that I get something that looks like K1. Okay, so since we defined the positive direction to be upward in the same direction as the centripetal acceleration, we have the sum of forces being the normal force at point A. Gravity is directed downward, so we have minus mg, and then that's all equal to our mass times acceleration, VA squared over r. Okay, so in order to make the right-hand side equation look like K1, actually be equal to K1, we can write r over 2 and a minus mg. Since we multiply both sides by r over 2, we get 1/2 mass velocity at point A squared. And then that's going to be equal to our K1. So we can then substitute this expression in for K1 at the end. We don't have to take the midpoint step of finding what the velocity at point A is. Okay, and we can do the exact same thing for point B. So we can write down our sum of forces at point B is equal to mass times the velocity at B squared over r. This time, the centripetal acceleration vector is pointed down, so that's going to be positive. So we're going to write down our sum of forces with respect to that positive direction. So we have a normal force at point B is directed down, so that's going to be positive. And we have our gravity that's directed downward too, so we have positive mg equal to mass velocity b squared over r. Okay, we can do the same thing. We get r over 2 normal force at point B plus mg equal to 1/2 mass velocity at point B squared equals K2. Okay, so we have K1, that's equal something that we just have in numbers, so we can solve that. K2, that equals something that's all numbers, we can solve that. Mg, so now we can find what the work due to friction is. So we can substitute that all in. We have our work due to friction is equal to our negative mg. Actually, let me write all that down again. So we have r over 2 Na minus mg plus work due to friction equals r over 2 Nb plus mg. And then we're going to have plus mg times 1. Okay, so now we can solve for our work due to friction. We have work due to friction is equal to mg. And then we have this quantity minus that quantity. So we have plus r over 2 Nb minus Na, and then plus 2mg. Okay, now we can solve this. We have work due to friction as a sum of things that are just numbers now. So we have work due to friction is equal to 0.3924 joules plus r over 2 Nb minus Na plus 2mg. We substitute in all those numbers, we get minus 0.6. And let me erase that positive just to make it clear. Minus 0.6213 joules. So that means we get the work due to friction is equal to negative 0.229 joules. That's our work due to friction.